discuss standard object in one-dimensional localization theory, density of states, Lyapunov exponent, statistics of the local static of the spectrum, but in the situation when potential depends on the heavy-tailed random variables. Corresponding problems I discussed many years ago, maybe 10 years ago, very actively with Zaslavsky in New York. George Zaslavsky, he died several years ago, and he was the editor of the physical journal Chaos, and he made a lot for popularization of the so-called Lviv light among physicists. And I returned to this topic relatively recently, mainly because of relation between stably distributed variables, fractals, and hierarchical structures, and so on and so forth. But I will discuss the following standard situation. We have some one-dimensional Hamiltonian with a potential, and we consider spectral problems that h psi is equal to lambda psi, x greater than equal to 0, it does not matter, and assume that we have Dirichlet boundary condition, zero boundary condition. And we consider potential one of two following simplest types. First type, when we have this number one, when we have potential of the form, we have bumps of the unit length with random amplitudes. 1 and here we have for n to n plus 1, so indicator and some xn, and n from 0 to infinity. But xn can be either positive or negative, two completely different situations, and we will assume that xn have heavy tails, namely not xn but square root of xn or something like this. This is the model number one, and second model will be when we have bumps of the, for instance, unit height, but between bumps we have very long gaps. So something like this, v of x is some indicator of between Ln and Ln plus 1. Here we have something like this. 0, 1, 2, 3, and so on. And but Ln, and again from 0 to infinity, but Ln in this case equals y1 plus yn, some positive random variables, and plus I will let n, because it's something like this. You have unit bump, and after this gap of the length y1, another bend, and another gap y2, and so on and so forth. This is two standard situations.
Still in
And
the second,
what?
still in the second case, xn IIDs, right? Still.
What?
In the second case, xn, the coefficients. Oh, you don't have coefficients.
Xn and yn will be in all cases independent random variables. Xn on some probability space, IID random variables with heavy tails, and the same y. And yn also. IID random variables with heavy tails. If xn, if for instance expectation of y is finite, that is the standard model in localization theory. This process is practically stationary, ergodic, and everything is okay. Here, situation not so clear, but everybody knows that standard assumption in the localization theory is that the expectation of the logarithm of the norm of some transfer matrix between some origin points into 0 and some n, this expectation must be defined. It means that transfer matrices, their norm cannot grow faster than exponentially. This is standard assumption on xn. It can be expressed in xn, and we will do this very soon. And but for such with situation with gaps, standard requirement that expectation of yn is finite. But instead of such conditions, we will assume that the xn or yn are heavy-tailed. In particular, they have no expectation, and so on and so forth. And I will discuss first of all model number 1. When it's exactly what is written here, and random variable square root of xn have density, they are ID, and they have density rho of x, which for large x has a asymptotic constant over x to the power 1 plus alpha. This is a half axis case, and x is positive if x goes to infinity. And alpha here is less than 1, which means that our bumps sometimes are very high. And in this case, as usually in localization theory, we want first of all to calculate transfer operator. I especially consider piecewise constant case. More general case also can be studied using quasi-classical asymptotic, but in this particular case, this mononomial operator T sub lambda, which correspond to our problem, from n to n plus 1, which transform psi function of solution of this equation and its derivative at the point n to corresponding value function and derivative at the point n plus 1. This, because constant coefficient, can be presented in the following form: cosine hyperbolic square root of xn minus lambda, and xn are positive, and here we have this square root of xn minus lambda times sinus hyperbolic square root 1 over square root the same argument sinus hyperbolic square root and cosine hyperbolic square root of xn minus lambda. Of course, xn minus lambda can be negative. It depends on lambda, but in this case, of course, cosine hyperbolic will be simply cosine. But in the situation when we have sometimes very high bumps, when xn positive, in this case, it's convenient to present in such a form. And normally, this operator, any norm, Hilbert-Schmidt or operator norm, does not matter. I will write down simply n in the future instead of n plus 1. Normally, this operator can be estimated something like this: constant, which depends on delta. For all n with lambda in some fixed interval delta, there are constants depending on delta only. That is, and square root of absolute value of xn, and plus another constant which depends on delta, because I have here factor. What?
You miss logarithm before the norm.
What?
The logarithm before the norm, or no? Yes, of course. Before the norm, you get, because you are hyperbolic function, so you need logarithm before the norm.
What?
Logarithm of the norm is less than,
Exponent of square root of xn.
sorry.
What? You, I did not finish yet my formula. Sorry.
I told you already logarithm.
Yes. This is, and this formula explains why we have square root of xn, why we need condition of xn. And if random variables are negative, it will be next model. That's instead of hyperbolic function will be trigonometric function and only first factor. But here, norm for large values of xn is extremely large. And that,
So, Stas, you want the boundary the other way, right?
but
You want this to be larger than this constant. You want the norm to be larger than that. This is what you're
yes,
saying.
yes, no,
Not
but this is
just
the upper estimation. But lower estimation is also working, but this is a bit more difficult.
Well, for T lambda n is the single one, or is the product of all up to
No,
n?
no, this estimation, of course, you can get this is equivalent.
Exactly.
But I'm talking about the monodromy operator between 0 and n, which is
Yeah,
a
of course,
product.
that's another story. Sure,
Yes.
yes, I understand.
But if we consider, as usually in spectral series or localization series, the question is how propagator growing on the long interval. Let us consider this T lambda 0 n. It's of course T lambda at the interval 0, 1, T lambda at the interval 0, 2, T lambda at the interval 0, n. And we must find logarithm the norm of T lambda 0 n divide by n, and in standard situation this goes to Lyapunov exponent. In standard situation it goes to Lyapunov exponent, it depends on lambda, and which are of course positive because of independence. This is standard fact in Spertenberg series, which exactly requires this condition, but this condition doesn't satisfy because square root of n has no expectation. And central fact in this model 1 is that central fact is that if I consider a logarithm of this norm, T lambda of the interval 0 and z, and divide by n to the power 1 over alpha, but not n, that it will converge only in the distribution in law to some random variable zeta alpha, which has stable distribution with parameter alpha. This is so-called positive random variables with the stable distribution. In standard probabilistic notation, alpha less than 1, but parameter beta of asymmetry parameter is equal also to 1. It means that, in fact, that Lyapunov exponent oscillate randomly. Oscillate, but it's around some more or less it's bounded in probability, but the function of n is random. And I will say several words how to prove this theorem. This is relatively simple fact. Namely, first of all, norm of T lambda of interval 0 n. Of course, logarithm this norm. It's smaller norm of the product, smaller than the product of the norms. Take logarithm, it is smaller or equal the sum of the logarithm norm T lambda. Okay, okay, from 1 to n. But this is what? Logarithm of this C1 square root of xk plus c2 plus square root of xk. And this guy has, of course, good expectation, and here exactly we have square root of xk, and after this you can apply standard theorem. Under this condition,
You have summation on the right in the last formula.
What?
In the very last formula, I think you forgot summation on the right. This is
I have summation, of course. You are completely right. Random variables square root of xn, they, due to this regularity of the tail, belong to domain of attraction of so-called stable law, and this is a standard fact. And this sum, first sum has order n, but this is n to the power alpha, which is 1 over alpha here is greater than 1. This is one of the effects of the heavy tails. But let us note that in this situation, in situation of the model number 1,
Yeah, but this is just
if-
operates.
what?
It's just operates. You claim that it goes just.
It's the same for the lower. It's the same for the lower because it's trivial. Because he uses estimates alone and
What do you mean the same?
I divide by 10, this is only an estimation from above, of course.
Right.
Yes, but estimation from below, it's a bit more difficult. It's nevertheless
Why is it more difficult?
requires, what?
I don't understand why it is more difficult because this estimate which you wrote should be asymptotic. I mean,
No, it's a product of norms.
No.
No, but
How do you
but
guess?
he wrote a sum. Right?
Yeah, sure, but you cannot lower bound the norm of the product by the sum. The product of
Ah,
the
that's
norm.
what you.
This is the other bound. Norm is multiplicative. So
No. This, it means that this is situation, this conversion law to the stable values, we need, of course, estimation from below, but it's also not very difficult. It's necessary to use so-called Darling theorem here, which tells that if you have random variables with heavy tails, that if you have a random variables with heavy tails, and you consider, for instance, total sum of first n random variables, that maximum term has the same size as the sum. If you take maximum term second n value, third n value, or for instance 100 biggest terms of variation sequence, it already will give you very good approximation of the sum with the accuracy 1 minus epsilon. But propagation through very high bumps, this will increase norm exactly with coefficient square root of xk because of phase, incident phase for the very high bump is more or less uniformly distributed. It's very difficult to find probability that solution will decay extremely small. This is standard technique. This is not very difficult. You can, after this, estimate this norm from below. It will contain again square root of sum of square root of xk, and it will finish the proof. But what happens if we consider so-called theta lambda of n? Theta is the phase of the solution. This theta lambda, if I divide by pi, it's okay rotation number. How many terms made phase for given fixed energy lambda when we consider solution from 0 to n? This phase will rotate very slowly if we have high bumps, but for the bumps of the typical size of odd one, it will be random. And in this case, to see that if we divide this theta lambda of n, I don't want to write down equation for the phase, standard Riccati equation, that it's easy to prove that it converges P almost surely with probability 1 to so-called n of lambda in integrated density of states. And nothing happened. This we don't need here that equation, the logarithm of the norm. A logarithm norm is finite. This is not difficult to prove. And secondly, and of course, n prime of lambda and small of lambda also exist because we made assumptions that there is density of the distribution of our potential, there is density of states, and there is local Poisson theorem for the eigenvalues in this case. Exactly, it means that, I will formulate it here. This is Poisson theorem. It means that if we consider number of lambda I n, we consider now our problem on the interval 0 n with zero boundary conditions. We consider number of eigenvalues of restriction of our Hamiltonian one-dimensional with Dirichlet boundary condition, which belongs to interval here lambda naught over n and lambda naught plus c over n. Lambda naught is a fixed positive energy, bulk of the spectrum. No, I assume that my random variables can be arbitrarily close to zero. In this case, spectrum will start from 0 to infinity. And then this guy has Poissonian distribution asymptotically, if n goes to infinity. Poissonian distribution with parameter is exactly n of lambda naught times c. Poissonian distribution. It's a standard theorem, and the proof is well-known proof. In the simplest form goes to Minami. It's work without any changes in this case. It means that for the model number 1, we have deviation from the standard theory in the Lyapunov exponent. Lyapunov exponent is random. It's more precisely, it's oscillate randomly, but density of states, local Poisson stratifies the same as in the standard series. Okay, let's consider now model when we have instead of high bumps, we have very deep wells. It's the same model, but I will change sign of the potential. And situation will be completely dramatically different in this case. Okay. This is the model number 2. We have minus psi prime and minus v of model number 1 of x, then psi is equal to lambda psi. We have something like this. We have negative wells, and some of the wells are extremely deep, because we also assume that random variables have the same, exactly the same density, with the same regular tails, and so on and so forth. In this case, Lyapunov exponent exists in the standard sense, because you see, our transfer matrix will contain sine and cosine, as somebody said already earlier. In this case, norm will be estimated exactly by this term only. There is no exponent, and after this everything is okay. There is standard Lyapunov exponent, gamma of lambda, which is greater than 0 for lambda. And but what about density of states? Or rotation number. Rotation number here does not exist. More precisely, it also will fluctuate. If you have very deep well, that solution of this equation, of course, can be easily calculated, and rotation number here will be of order square root of xn minus lambda, absolute value now, over pi. You have here, which is of course more or less equivalent for large values of xn, square root of absolute value of xn over pi. And as a result, that theta lambda on the interval 0n over pi, its total rotation number of the zeros of the typical solution, plus minus 1, will be exactly like before, square root of sum of xk, k from 1 to n, plus something of order 1. And again, it's just absolute value, sorry. That's exactly the random values which we discussed before. And it means that if I will consider this guy and divide by n to the power 1 over alpha, then it will, like before, it wins in log to the what, some beta alpha. The same positive, stably distributed random variance. It means that integrated density of state does not exist after standard normalization. It's exists only in some mean value. It's fluctuate, and mainly, especially, it fluctuates strongly when we have very deep wells. I said already that in this sum, according to Darling theorem, the main contribution gives several biggest terms. It means the deepest well, or maybe 2-3 deepest wells, give already our main contribution to the n of lambda.
This should also hold if lambda is negative, right? You wrote the condition that lambda positive, but this
No,
should
no,
be,
no, lambda can be, doesn't matter.
yeah, but you, okay. for
Lambda
everybody,
lambda belong to some fixed interval data. It can
Exactly.
be negative
And-
or positive, doesn't matter.
Exactly.
The operator itself,
But
the operator itself, it's still limit point case or not?
what?
The operator itself, что it's still limit point case or?
Yes, this is a good question. If we consider arbitrarily identically distributed random variable, does not matter. This heavy tails is not heaviest possible tail. You can consider arbitrary heavy tails. And in this case, potential along some sequence of the wells will decrease arbitrarily fast. Nevertheless, it's essentially self-adjoint. Because of Hartmann theorem, there is remarkable Hartmann theory which tells that if you have arbitrary potential, but not arbitrary, but there is sequence of the unit intervals where potential is bounded uniformly from below along this
By
interval.
squares.
No, for instance, positive.
Yeah, but by squares minus x squared.
No, not. If you have system of the intervals where potential is bounded, no, for instance, unit intervals, when potential is bounded from below some constant sigma. This is not close to generalized, you can assume that it's positive. But otherwise, this intervals can grow to minus infinity as fast as possible. Quantum particle has finite speed on such intervals, and the result, it cannot reach infinity in the finite time. This is the Hartmann theorem. You can even make such intervals narrow. They can be smaller and smaller, but in this case, of course, it will be some additional restrictions. But it's very physical theorem that operator one-dimensional operator. The same is true in multi-dimensional case also. It's quantum mechanically completely in one-dimensional case. If we have a system of unit intervals along which is bounded, and of course, because we have ID random variables that will be bounded. Okay. But Lyapunov exponent is positive, density of state doesn't exist. However, what is very important, that this term is independent on lambda. This is only leading term of asymptotic. Dependence of lambda must be taken into account. It's possible to prove that this is regularization. We can consider regularization of this rotation number. If you can consider theta lambda over pi and subtract sum of square root of xk, k from 1 to n, then this already converges to some limit n star. And this limit will be non-random and so on. This is a new density of states. You see, physical idea is very simple. If you have extremely deep well, then there are many eigenstates located here. But we are interested in only eigenstate in some bounded interval. We can remove all of them. In reality, it's possible to prove that if you truncate too deep wells, that you will not change statistic of the spectrum in the bulk locally. And but nevertheless, this is difficult. This is one of the most difficult results in this area. And because there exists this in star of lambda, there exists local Poisson theorem. One can think that there is no local Poisson because we have deviation from the existence of the integrated density of state, but this is only illusion. This is the model number 2, and we have here Poisson statistic. We have everything is okay with Lyapunov exponent, and of course in both model 1 and 2 we have localization, exponential localization. In model number 1 we have not simply exponential localization but super exponential localization. Eigenfunction decay faster than exponential with exponent negative n to the power 1 over alpha, roughly speaking. Okay, but let us consider now a situation when we have bounded bumps, but long gaps in between. In this case, we have another effect, and it's again some of those effects can be proven easily, some are a bit harder, but this is classical probability, classical limit theorem. Let's consider model number 3. And we have exactly as I told you, unit bumps, and we have y1. And y2. We have our, in this case, not difficult to prove that because the sum y1 plus yn plus n over n to the power over alpha will tends to the same zeta alpha in log. It means that distance between 0 and n bumps is growing faster than linearly. Then in this case, one can easily prove that what is the Lyapunov exponent here? The question for the, what is the Lyapunov exponent here? You see, between bumps, magnitude of the solution cannot grow. It's constant. It can
It should be zero.
go only after interaction with the bump. We have n bumps. After n bumps, solution can increase at the exponential of n. But the distance between
It's less
0 and
than-
n bumps growing n to the power 1 over alpha. Alpha less than 1 is faster. It means that Lyapunov exponent here is equal to 0 identically. Usually Lyapunov exponent. If you consider t lambda of 0x or some x, take logarithm and divide it by x, that will tends to 0. P almost sure. Simply because, I repeat one more time, for solution of equation h psi minus psi prime plus v psi equal lambda psi, I consider lambda positive. Solution of this problem between bumps has constant magnitude 1. It can grow only after repulsion with the bump. Total growth of the solution is equal to number exponent to the what? Number of the bumps inside the interval 0x, which is growing at the x to the power alpha. And what is theta lambda of x over x pi x? This is the phase. What is it? No. Look, between bumps, phase has standard behavior. It's rotate with the speed square root of lambda. But area covered by the bumps is O small of x. And as a result, theta of lambda, in this case, tends to square root of lambda, for positive lambda, if it goes to infinity. It means that Lyapunov exponent tensor space looks like for the standard second derivative, but of course it is not true. We must consider Lyapunov exponent in the different scale. And situation here is very similar to the old paper of Katani. Katani isn't here.
He is here.
Katani studied with his students situation when we have second derivative and random potential modulated by decreasing factor. For instance, v of psi of x over square root of x. Psi of x, best possible potential. But in this case, if potential is not square summable, the rank generalized Lyapunov exponent, not with the standard scale x, but x in some power. And here we have something like this, but nevertheless it's not Katani situation. If you consider, for instance, t lambda monoid imperator between 0 and ln plus 1. This is our transfer matrix or propagator after n bumps. Then, if you take logarithm of this, logarithm of this norm and divide by n, then you can apply usual subadditive limit theorem, and it converges exactly to some gamma tilde of lambda which is greater than 0. But I divide by n, but ln growing as it was written here, this exactly ln over n to the power our alpha. ln has order n to the power alpha greater than 1 over this is, but nevertheless this Lyapunov exponent, which exists only again in law. In the case of Katani, when potential decreased physically, this potential is decreasing in some mean sets. because the number of the bumps is smaller and smaller and smaller. Concentration of the bumps of decreasing. But nevertheless, it's a bit different situation. In this case, Lyapunov exponent, after this such normalization, after probation of the bump existence, strictly positive, and it's enough to prove localization theorem. Like in the situation which Katani discussed earlier, in this case, there is localization, but eigenfunction decreasing not exponentially, but some exponentially, with some fraction exponentially. And the same situation with density with rotation number. Again, it's possible to consider regularization of the rotation number. It's possible to divide contribution to the rotation number of these bumps and the rest. It's possible also to construct, I have no time to discuss this topic, it's possible to prove that if we subtract from this guy leading term of asymptotic, pi x square root of lambda, then the rest after another normalization, n to the power 1 over alpha, has limit in law. Limit in law, in this case there is no density of states, even after regularization. It has only limit in law, and in this situation, there is no Poissonian statistic of the spectrum. But I don't know what did you prove in whole paper, or maybe Minami proved later, assume that we have decreasing potential. Do we have, in this case, Lyapunov as Poisson statistics?
If we are considering with Nakano right now, if alpha is critical, the decaying order is one half, then one can...
No, one half, I understand, this is a borderline case.
Yeah,
Yes.
but if alpha is smaller...
But here there is no Lyapunov statistics at all, and it's possible to explain without any physically. Because with positive probabilities, one of the biggest, let's consider first n bumps. They separated by the gaps. One of the gaps very long, which is comparable to the total sum of all other bumps. But with positive probability, this maximal gap can be equal, for instance, 99% of the total length of all bumps together. But in this extremely long bump, which we have with positive probability, that difference between lambdas will be the same. It will not change. As a result, density of states in this scenario will demonstrate arithmetical natures. We will see strong repulsion between.
Yeah. This is what Kotani was about to say.
Yes,
this is
yes,
the case,
yes.
exponent less than 1/2, and you get clock behavior.
Yes, yes.
Right?
No,
Rather than 1/2, sorry, larger than 1/2. Yes, larger than 1/2.
No,
It's
but-
fast enough.
Larger than one half, because this is a situation when we have coexistence of a continuous spectrum and point spectrum. This is it's
No,
borderline.
the model is different because here what you're.
But
Oh,
they,
yeah, you're
but
right.
they
Okay, so
have,
this
but
is
they
not
have,
a-
nevertheless, they have non-standard normalizations. They have usual, they have usual density, density of state, and they have Lyapunov exponent, and so on and so on. Okay. In this case, Lyapunov exponent is positive with a different scale, which leads to the fractional decay of eigenfunctions, that we have no, we have trivial density of state or trivial n of lambda. But again, after appropriate regularization, you can find true n of lambda, and there is no Poisson statistics here. And the model number 4, I want to combine together. It's possible to combine together all three effects, but I will not discuss this topic. I will discuss this model number 4 in one particular case when we have very strange phenomenon. Assume that we have the potentials will be bounded here, but this we have x naught height of the first bump after this y1, and again you have x1, and I have y2, x3, and so on and so forth. And assume that all random variables x1, x2, that is height of the bumps, are independent from the gaps, and assume that both of them belongs to the domain. Assume the square root of x. It's has density probability square root of x greater than x, and will declare constant over x to the power alpha, and probability that y greater than x also equivalent constant over x to the power. The same alpha. In this case, we have the following situation. What will be monodromy operator in the monodromy operator at the point Ln? Let's consider logarithm norm of T lambda from 0 to Ln plus 1. It means that I consider n bumps, but bumps now are very high. And if I divide this, as I said, this is the same as what? It's, and our alpha, it will be the same argument as before, it will be the same equivalent to the sum of x1, blah, 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 square root of xn, or n to the power alpha, and it will tend in law to some zeta alpha. But y1 plus yn plus n, which is exactly my Ln. If I divide by the same n to the degree of alpha, and the degree of alpha, it also will tend to what? It also will tend to zeta alpha. I will take t, it's another accord, zeta alpha. But with the same alpha, it means that lengths distant from 0 to n bumps growing n to the power alpha. And Lyapunov exponent is growing n to the power alpha. It means that it's exactly, we have equilibrium between two effects. We can expect that in this case, one can expect that in this case we have Lyapunov exponent, true Lyapunov exponent, because normalization must be here simply by the lengths. But it is not. And this is easy to see. If you can divide by Ln, logarithm of this norm, between 0 and Ln plus 1. And divide by Ln. Then of course you can divide by n to the power alpha here and here, pass through the limit, and it will tend in law to very strange object, ratio of two independent stable random weights with parameter alpha. It's also in the Darling theory of extremes, for such it also appears such kind of object. There is no here density, there is here in this case fluctuation of rotation number. You can estimate rotation numbers here. Nothing happened with rotation number here. Rotation number in reality here in the mean approximation will be simply square root of lambda times ln. But analysis shows that in this case there is no Poisson statistics. Statistics is highly non-trivial. We did not finish such calculations. This is more or less what I wanted to say about one-dimensional theory. And now I have 10 minutes. I will want to discuss a bit multidimensional case, where the situation is not clear at all. What is very important here in all these constructions, it's very important that if you have very high bump or very deep well, then this object divide straight line into intervals, which are independent on this guy. It's very important that one-dimensional lattice is so-called non-percolating graph. Probability that bump is very high is, of course, extremely small. But if such barrier sooner or later will appear, that it will give strong effect on what? On everything, on the density of states if we have negative, very deep well, or on Lyapunov exponent we have positive, very high barriers, and so on and so forth. But in multidimensional case, let's consider the following situation. We have lattice ZD, and we have Hamiltonian delta, it's standard Laplace operator, sum of the nearest neighbors, plus V of x omega, and assume that V of x omega is the summation xi of xl sum delta x minus xl, L from 1 to infinity. We have here two type of randoms. First of all, we have random magnitude, like here, and also we have point xl. If you consider point xl, for instance, which have some Bernoulli distribution, or given by Poisson point process or Bernoulli field, that it will be, of course, usual multidimensional lattice Hamiltonian, where unfortunately we know everything only if the coupling constant is large. But if coupling constant is small, that unfortunately we do not know what happens in this case. But assume now that XL are very sparse. They can be random. For instance, we can consider Bernoulli field. We can assume that probability that X belongs to this gamma. Gamma is the set of all these centers. XL. The probability that X belongs to gamma will some function phi of x, and which tends to 0 if absolutely x goes to b. In this case, concentration of such point XL will be smaller and smaller and smaller. But XL can be very large. Because multidimensional lattice is percolating lattice, it means that if we consider independent set of the point which concentration is small, smaller than critical threshold, then they will not separate space from the disjoint chambers. We have some isolated islands of such XL, and quantum particle can easily move between such barriers. And it's exactly was the central point in Anderson's argumentation, physical argumentation, why he expected delocalization for small coupling constant in high dimension. Here, assume that XL are very sparse. That it doesn't matter what is the magnitude of XL. XL can be with arbitrary heavy tails, that it cannot destroy the absolute continuous spectrum. If not very difficult mathematical fact which goes under different condition to Krishna, Kirsch and other, tells that if XL is sparse enough, doesn't matter what is XL. XL can be equal to plus infinity, which means that at the point XL we simply must impose zero boundary. In this case, we will get absolute continuous component of the spectrum. Spectrum on the spectrum of Laplace operator will be absolutely continuous. Outside, of course, because we have very high bumps, we can get point spectrum, dense point spectrum, some kind of coexistence point and absolute continuous, but this is not, of course, this is a toy problem. It's not true Anderson problem. In multi-dimensional case, because our random variables for sparse centers with such centers cannot we cannot organize barriers which will stop propagation of quantum particle to infinity. In this case, absolute continuous spectrum for low concentration is typical. It's independently on this guy. But in the same situation with n of lambda. N of lambda for sparse will be the same like for Laplace operator. And there is no, it's not clear how to introduce good renormalization here. It's exactly 2 times to stop.
Okay. Thank you. Any questions or comments?
Maybe I don't know this, but in the first 2 models, if they are combined, the X allows you to have both positive and negative X.
No, it is, yes. Model number 4 in reality contains very high positive peaks and very deep wells, and in this case all 3 effects will be together. They in some sense separated, because I repeat one more time, Lyapunov exponent depends only on the very high peaks. If you have abnormal density of states, it depends only on what? Or very extremely deep wells, which
There was some kind of mixture of the...
Yes, everything. But with Poisson statistics, situation is more complicated, because I said you that I can consider in this model number 4, I can consider that here alpha 1 and here alpha 2. And in this case, sometimes we have local Poisson statistics, sometimes not. It depends on the relay, but I have no time for such details. Yes, all this theory more or less can be moved to the fractals. Classical fractal like Sierpinski lattice, or they have the fundamental property that if you can find finitely many bumps, extremely high bump will effectively separate infinity from the rest, and after this it's lead first of all to localization. It's not one-dimensional localization, it's already dimension of Sierpinski lattice between 1 and 2. But I expected the second talk about so-called fractal non-percolating graphs. This is related ideologically to all this stuff. But nevertheless, it will be some graphs, and I will discuss mainly the problem that, which I cannot solve in full generality, but but I have already some particular successes. The conjecture is that for all, at least for white class of the graph with spectral dimension less than 2, we have localization for arbitrary coupling constant. It's proven in under some, for some, first of all, not very general, but some specific graph, but white family of the graphs. It will be already, in some sense, multidimensional theory.
More questions or comments? Well, if not, let's thank class again. But next week.